But if you look at sort of the individual fibrils that are there, you can see this is 200 nanometers. So you can get things which are 200 nanometers in length and maybe 10 nanometers across, or even 5 nanometers across. And in composites theory, the aspect ratio of your fiber really makes a huge difference. Okay, and so these are high aspect ratio renewable fibers, but they're available at the nano scale. That's a great question. I'm not sure I'm completely qualified to answer it, but I know that there has been work ongoing to look at all of those issues, and I think that they certainly look better than non-degradable materials. I almost had a perfect answer for you, but unfortunately I was collaborating with Howard Fairbrother at Johns Hopkins University, and we had all these samples ready for biodegradable testing, and we killed his compost. We didn't make him very happy as a collaborator. And it turned out it was because the student had used mold release agent, and so he had sprayed Teflon on the mold before he made the samples, and so the fluorine got into the compost and made us unpopular at Johns Hopkins University. I haven't been invited there for seminar. But here, just to show you, I mean, they're making these at the pilot scale now. You can call up the University of Maine, or actually go on their webpage and fill out a purchase order. You can get a 5-gallon bucket of nanocellulose for a few dollars a pound. And these are those two initiatives. And so I feel fortunate to sort of be involved in both sides of that, both the biomanufacturing, the bioplastics, and the nanocellulose. Is there another question? No? So here's the issue that you run into when you're doing nanocomposites, or really lots of different types of things. If you want to make a good nanocomposite, you need to disperse those nanoscopic fillers everywhere. It doesn't do any good if there's just a big sort of ball of them in the corner of your material. And so in the classic sort of mixing literature in polymer engineering, people talk about distributive and dispersive mixing. So that is, you can distribute your filler everywhere, but if it's still agglomerated, it doesn't necessarily do you any good. Or you can disperse your agglomerates, right? But if they're not distributed everywhere, you also won't have a particularly effective material. And so the key here is to have both good distribution as well as good dispersion. And of course, if you want to get good dispersion, an easy way to do that is through manipulating the surface chemistry. And so the idea that we had is to actually decorate the cellulosic nanowhiskers with polylactide chains. Okay? And here I show the chemistry associated with the ring opening coordination insertion mechanism of using just sort of the traditional tin type of catalyst. And the details of the chemistry are not so important, but you should understand that really the initiator is what you'll find at the end of a chain, and it's initiated by an alcohol or a hydroxyl group. Okay? Well, if you know the structure of cellulose, you'll know that it has lots of hydroxyl groups associated with it, and so our idea was, can't we take this cellulosic nanowhisker and actually grow polylactide chains from it? And so we've been able to do that. And I would say again, this is sort of if we think about the advances in industrial biotechnology or industrial ecology, also we're getting better at doing polymer science, and so we're getting better at manipulating these types of nanoscopic systems as well. Okay. And so we had to do a lot of work to really get this to pan out the way I had originally envisioned it. And we said, okay, we'll make some cellulosic nanowhiskers, and then we'll polymerize polylactide. So we made cellulosic nanowhiskers by the usual sort of recipes that are in the literature, just sulfuric acid. Okay, you get your nanowhiskers, you maybe dialyze a little bit, put it in with the lactide, polymerize it, turn jet black. Just terrible stuff. Okay. Eventually, we figured out, hey, it's the sulfite ester groups that are on the cellulose chains that are killing us there. The thermal stability is poor. So we started making the whiskers instead with hydrochloric acid, and then at least it didn't turn black, but when we did the polymerization, we just got like sort of a powder. And if you do polymer synthesis at all, when you have just sort of powdery stuff, that it's very low molecular weight. And so as we looked at those materials, they had terrible properties. And so we really had to come up with a better way of making the cellulosic nanowhiskers. And what we sort of got to through, the typical type of research path of going here and going there was the fact that you could sort of do a one-pot, single-step methodology by combining the hydrochloric acid with an organic acid. And so when you do that, not only do you hydrolyze away the amorphous regions of the cellulose and leave behind the whiskers, but you also do an esterification reaction on the surface, and so you're simultaneously doing the surface decoration. And so here I show that with acetic acid. So we're really just making cellulose acetate in this particular case. But we've done this with all kinds of different acids. So you can do it with butyric acid, although that's kind of stinky stuff. Yes, we do it with lactic acid, in fact. And I'll show some examples of that later. So the nice part of this, and we've also practiced this chemistry, which is a much greener chemistry than the way typically people functionalize carbon nanostructures. So in this green chemistry paper, we do this both on cellulose, but also on carbon nanotubes and buckyballs as well. Again, I like to be as quantitative as possible. And what we're trying to do now is to control the surface chemistry. And we need to quantify that in some type of a way. And what I'm showing here is a comparison between cellulosic nanowhiskers made with just hydrochloric acid and cellulosic nanowhiskers made in the presence of hydrochloric acid and acetic acid. And you can see this difference here in the FTIR spectra down here, and that's the acetate group. So the absorption at 1736 wave numbers is the absorption due to the acetate group. And in addition, there's absorption band at 1162, which has to do with the cellulose structure itself. So if you take the ratio of those two, because FTIR is quantitative, what you've done is you've counted how many acetate groups do you have per ring in your cellulose structure, okay? So you're counting acetate groups to total amount of cellulose. Well, that's not what we really want to know, right? Because what we really want to know is how many acetate groups are on the surface, right? So now I just sort of know acetate groups to volume of the nanowhisker. So now what do I need to figure out? I need to figure out the surface area to volume ratio of the nanowhiskers themselves, and then I can convert from number per volume to number per surface. And so what we turn to do that is light scattering, and this is multiple angle laser light scattering, a very common tool for polymer scientists. But if you're not familiar with it, it gives you a lot of information. So we're looking really at the scattering at a bunch of different concentrations here as a function of the angle. And there's really three pieces of information that come out of there. One is to do with sort of the thermodynamics, the interaction of the dissolved material with the solvent. The other is a measurement of the absolute molecular weight, the weight average molecular weight. And the final part is to do with the radius of gyration of the material. And so you probably can't read these numbers, but down here it's telling me that the molar mass that we're measuring is 3 billion grams per mole, okay? 3 billion grams per mole. So again, this is at the nanoscopic type of level. This is really a supramolecular assembly. The technique is perfectly fine for doing small particles like this. It still holds and still is giving you the weight average molecular weight, but it tells you something about the size of the structures that we're dealing with. Of course, the other thing that it gives us directly is the radius of gyration. So in here it says that the root mean squared radius of gyration is 220 plus or minus 8 nanometers. And so we can think about these nanowhiskers as being either cylinders or spheroidal ellipsoids. And it turns out, because it's crystalline cellulose, we know the density. And there's just a simple cubic equation, which comes from a mass balance here if you know the molecular weight. And so you can actually get at the length to diameter ratio here, i.e. the surface area of the spheroid, by simply measuring the radius of gyration. And so now we do know the surface area to volume ratio for our materials. And so that means that we can actually control the number of acetate groups on the surface, which is really what we're after. And why are we after that? Well, I take it Travis teaches polymer, yeah? So I should ask all of you that have had Travis's class, why is that so important? Well, the issue is if you have a lot of initiating groups compared to the amount of monomers you have, and each initiating group starts a chain, then the monomers per initiating group is a low number. It's a small number. And so you get low molecular weight. And so, of course, that was the problem that we were having when we first tried to do this, even with the hydrochloric acid-derived cellulosic nanowhiskers, we just had too many hydroxyl groups. And so, of course, we were making, cruddy polymer, crumbly polymer would be a better explanation of it. It's just, it's low molecular weight. But now we really had all the tools in place. We'd characterized the nanocellulose, we know how to control the surface chemistry, and we can actually dial in, how many initiator groups should I have in order to really get a high molecular weight material. And so we were able to do that and grow some very interesting materials. Here is, again, the infrared spectroscopy. And I'm a big stickler with the students for doing control experiments, right? And so in this particular case, you really have to worry about, have you successfully attached the chains to the cellulosic nanowhisker, okay? Because if you just sort of say, oh, here's FTIR, and I see both acetate groups and ester groups, so they must be attached. No. So if you remember from things like your catalysis courses, we make a distinction between physisorption and chemisorption, right? And what we're trying to do is we're trying to accomplish chemisorption, where it's actually covalently bonded to the surface. But of course, physisorption takes place as well. There's all kinds of mechanisms for polylactide to interact with cellulose. And so we have to make sure that we're doing better than physisorption. So as a control experiment, we just mixed up the nanowhiskers with preformed PLA of the same sort of targeted molecular weight, isolated that material, and washed it repeatedly with solvent until we no longer saw any change in the FTIR. Okay? And so we did that both with what we thought were chemically grafted as a comparison. And what you see is if you take the ratio then, in this case, of the ester to hydroxyl intensities, in just the native whiskers, this is only 0.24. But if you go up to A is for adsorbed, so that means physisorb by that case, it does increase to 0.34. So definitely some PLA is just sticking to the material by physisorption. However, if you then look at our grafted materials, it's 4 times larger. Okay, and so there's a very profound difference. We genuinely are getting physisorption. And of course that translates, we get very nice properties, modulus versus temperature. So if we think about sort of comparing these guys, if I have just my regular PLA, its modulus is on the order of 10 to the 8th at 100 degrees C. This is that glass transition temperature. It's on the order of 10 to the 9th when you're down at room temperature, i.e. where you can use it for cold food packaging. And now if we look at filling this up with my nanowhiskers, now at 100 degrees C, I'm almost matching the modulus of the unfilled PLA. And of course, that translates itself into that heat distortion temperature that we talked about before. And so now if I look at sort of my heat distortion temperature versus loading, this is increasing, and it's increasing quite rapidly. It depends if you do this in bulk or solution. I think when we do the solution polymerization, we just get slightly better dispersion. But you can see at 10% loading, we're able to get above 100 degrees centigrade. And of course, that's sort of the target for many different applications because you can hold boiling water at that point. So you can do sterilization and all kinds of things. And so here then is just sort of a picture of the nanocomposite in the middle. And you can see that we've done a good enough job through this sort of nanotechnology approach of controlling the chemistry to get the nanowhiskers so finely dispersed that the material does remain transparent. So patented that. So I alluded early on in my talk to the importance of being able to control stereochemistry. And in polylactides, that's particularly important. And that's because, as I said, with the genetically modified organisms, we can now make the D-lactic acid and the DD-lactide. Well, it turns out the handedness in the monomer actually translates itself into handedness in the crystallization. So if we look at the way polylactide crystallizes, the all L material will crystallize in a right-handed helix, and the all D will crystallize in a left-handed helix. And so we have a sort of a unique phenomena known as stereocomplexation. And so this happens even with the monomers. If you take LL and DD lactide, the melting point goes up. If you think of your usual eutectic, 2 crystals, and there's a melting point depression, here it actually goes up in the middle, and at 50-50 it has the highest melting point. And that's because you form a crystal structure where in this case, the helices can just pack together better. It gives you a more stable crystal structure. And of course, if it's more stable, it's harder to melt. Okay? And so your melting temperature goes up by 50 degrees centigrade. And so our idea then was why not combine sort of our supramolecular structures with this other way to control material at sort of this nanoscopic scale and incorporate this stereocomplexation. So now I could, decorate my chains, say with poly D lactic acid, and then embed them into poly L lactic acid, and I should form material with an even better melting point. Thanks to Travis here, we were able to characterize this using the SAC system here, and just looking at the long spacing in terms of the crystallinity, and certainly this is consistent with the literature with what one expects to see when you do get stereocomplexation. Here's an even easier way to understand that. We're just looking at melting points. So at the very top we have the all L, and you can see the melting point is around 180 degrees or so. If we make the all D, we again get 180 degrees. But if we mix those two in a 50-50 mixture, we get the stereocomplexation. We didn't get the stoichiometry quite right. There's a little bit of homopolymer melting there at the same 180. But here's the majority of the melting is taking place up at 230 degrees C. So that's that 50-degree rise in melting temperature that people take advantage of with polylactides. Now, if we look at sort of our grafted nanowhiskers embedded in the complementary, we also get this much higher melting point. But we also have the rigidity associated with the nanowhisker. So again, we worked with actually with sealed air in this area to make some cups, and their interest is in microwavable food packaging. We all take these things for granted. There's so many scientists out there working on many things, but if you think about the material requirements for, they own Stouffer's frozen food and lean cuisine and these types of things. But if you pull your frozen dinner out of the freezer and it slips out of your hand and it falls on the ground, you need to have very good crack resistance at 0 degrees C or colder, right? So the material has to be able to be impacted at very cold temperatures. Then you take it and you put it in the microwave and you heat it up 100 degrees. So now it has to have dimensional stability at 100 degrees centigrade as well. And so, it's really incredible that, we have materials that will do all of that. And it was really, much more demanding than you might think to get this to work. And so let me just show you here. I have a little bit of a video on some of those materials that we developed on the more commercial side of our work. And so here I have one of those beer cups, and I've trimmed it down and putting some weight on it to show that, okay, it can support a load at room temperature, which is what you'd expect if you have a plastic material with a typical glassy modulus of a gigapascal. Get out the tea kettle and pour it in there, and let's see how it holds up to the load. Well, it's not going to hold up to the load at all, right? And so that's really the issue with any type of hot food packaging. If I put that on now, it's just going to sort of smush. I mean, it's above its glass transition temperature. I guess it could make for a pretty good practical joke, but not really something you'd want to foist off on your customers for hot food packaging. So now here's our nanocomposite material. It's pigmented black because that's what the sealed air people wanted. If you get a frozen food tray, it'll typically be black. We have them in green as well. We thought the green would be great and highlighted that it's green, and they were like, no, we just want it black. So I get out the tea kettle here. You don't see it steaming here, but it came right off the thing. It's still 100 degrees C, and I will demonstrate that in the video here because I'm saying, oh, here, soak through, and then I go, ow, I really hurt myself there. So I am burning myself with the water. It is actually hot. And I'm just giving it time for the heat transfer to take place, for it to thermally equilibrate with the hot water, and there you can see that it will easily hold that ½ kilogram or so load. So that's a reasonable success for us. We've been able to practice this on other nanofillers. So, the cellulosic nanowhiskers are nice because they're degradable, but they are a little bit expensive. So other things are less expensive. And this is just showing the same type of thing. We can get the stereo complexation. So, as material scientists or materials type people, it's all about structure property relationships. And so I had the idea, I was like, well, I know the heat distortion temperature goes up with crystallinity. Heat distortion temperature goes up when we put crystalline nanowhiskers in there. Heat distortion temperature goes up when we put rigid silica in there. Is it just, the rigid volume fraction that dictates the heat distortion temperature? And so here's different types of fillers, and the idea is, it does correlate with that. There's no doubt about it. But the correlation is fairly poor. If you look at the spread here, you can have maybe from 90 degrees to 110 degrees at roughly the same filler. And so it turns out that the morphology of the filler itself is very important. And as I alluded to before, high aspect ratio fibrous materials are typically much better than spheres. And the reason for that, you can think about sort of that log jam effect. There's a percolation threshold as you go to higher and higher concentrations, and when you have long aspect ratios, the percolation threshold is dramatically pushed to lower and lower volume loadings. And so here we're just doing a comparison, and it's a comparison of the cellulosic nanocrystals versus the silica, and you can see at comparable volume fractions, this is about 12 degrees better or so in its heat distortion temperature. So nano is cool, but not all nano fillers are created equally, I guess is the take-home message. So I mentioned bioamber and the fact that they're making PBS, and that makes a very nice material to blend with PLA. And in fact, if you think in terms of stiffness versus impact strength, you can get all kinds of different properties depending on the relative amount of PBS versus PLA. But that's a typical trade-off curve. And so what we'd like to do is move in that direction. And I know I'm running out of time here, but I will just hopefully convince you that we've been able to successfully do that. And so this is a blend that's 85% PLA, 15% PBS, and then either 25-10% of the cellulosic nanowhiskers. And you can see we can, again, push that modulus up, okay, as a function of temperature. So if you look at 80 degrees here, we're pushing up the modulus and in addition having things. And so it really starts to get complicated. We have the two homopolymers of PLA, so there's a melting temperature at 180 degrees, but they stereocomplex, so there's a melting peak at 230 degrees as well. And now we've put in PBS as well, so there's a melting peak down at 105 degrees as well. And so if you think about making this witch's brew, we have 6 separate phases present now in our nanocomposite material. And so we're still working to sort that all out. What does the organization and the structure really look like? But in the meantime, we use the usual types of tools. Impact testing, that's always a fun test to do. There's non-destructive testing and destructive testing. Destructive testing is always a lot more fun to do. You get to break things. And so here you can notice that we work at a university because the way we keep the flying bar from flying across and taking someone's eye out is with this sophisticated cardboard box here in the back that catches the piece when the hammer swings through. And so again, the idea here was can we improve the ductility? Can we improve the toughness of the materials and still maintain the heat distortion temperature? And in fact, we were able to do that. So you can see here our heat distortion temperature is higher. We're not quite as good as the blends, but we're better than just PLA. So now we've improved two sets of properties at the same time. We've made plastic forks out of that. And so just to conclude, really this whole area of biomanufacturing, and I've really focused on plastic materials, but adhesives and sealants and paints and coatings and I guess carpet sort of falls in there. There's really a lot of stuff that can be done because I think these things are coming together. And we've been able to sort of make nanocomposites that also incorporate stereocomplexation and control matter at sort of a particular length scale between 10 and 100. And I think that this is really, there is commercial potential here associated with the types of things that we're doing. And then just as a sort of a final remark, go back to acknowledgement. So this is after the hike here. There's another sort of not only group, but almost department-wide tradition of going to the Coors Lab, which is what the grad students call the tasting room at the Coors Brewery. And so after the hike, we went there, and just a shout out to all of you that are grad students. I mean, you're really the people that make things happen. And certainly myself as a faculty member would deeply appreciate your efforts. And so with that, I'll thank all of you and happy to entertain questions.
Let's go ahead and we'll get moving out so that class can come in. Maybe John can hang out for a few minutes, answer questions.
Yeah, I'll be in the hall.
Before we scooch him off for lunch.
Sounds great.